And I don't continue until the class says good morning. Now, next, are there any questions? All right, now, about half of what I talk about today is going to be on the exam. No questions?
I have a very basic question. I just wondered in the calculations that you did yesterday, did you take Doppler shift into account? Did you take Doppler shift into account? Because
did I take which into account?
Doppler shift?
Yes, I think everything was taken into account in all the calculations that I did, yes.
Okay.
Yes, it was hidden in there, and yes. All right, what I want to talk about today.
So the potential that you drew yesterday was...
the potential?
Yeah, I think it was
V.
R minus 2mg, right?
R minus 2mg over R times something over L times L plus 1 over R squared and minus something over R cubed.
So at the horizon, it was 0?
Yeah, at the horizon, 0.
So does that mean that, like, if you have this heat bath of quantum states, that they just flow?
If you have this bath?
Like, heat bath of quantum states, that they would flow just right over the horizon without any trouble?
Well, don't forget, in coordinates, let's take the tortoise coordinates. The tortoise coordinates, the true mathematical horizon is infinitely far away. So in tortoise coordinates or any other, and the tortoise time is just ordinary Schwarzschild time. So that's an example of the fact that in Schwarzschild time, it takes an infinite amount of time to cross the horizon. And that includes not only the things that you throw into a black hole, but also the things that form the black hole. The picture you should have is that from the outside, the black hole is a series of layers of Lorentz contracting sediment that gets closer and closer and closer to the horizon, flattening out, slowing down because of a combination of Doppler shift and time dilation. And the picture that you might have in your mind, at least classically, is that the black hole, as seen from outside, is a collection of objects that fall onto the horizon, and as they fall onto the horizon, they flatten out, slow down, and form a kind of sedimentary layer that never passes the horizon from the point of view of Schwarzschild time, or from the point of view of the observations of the distant observer. Quite in contrast with the perceptions of somebody who takes a ride through the horizon, who calibrates their watch, and according to their watch and according to their measurements of the mass of the black hole and all the calculations they do, they find out that they cross the horizon at 12 p.m. or whatever time it is. Now, what I want to talk about today is, first of all, a little bit about the notion of a stretched horizon, a little bit about the electrodynamics of the horizon. I'm not going to do too much about it, just a very, very brief observation about it, about the way electric charge distributes itself over the horizon as it falls into a black hole. And then I want to move on to the subject of information. Information is a very interesting subject, which I am not an expert at, but I know a little bit about it. And I want to talk about those things which I think are most important to the black hole physicist who's trying to understand the basic quantum mechanics of black holes. What black holes are is they're incredible reservoirs of information, the densest possible reservoirs of information, and that may be their best definition. They're the most concentrated form of information that you can imagine according to the laws of physics. They have 1 bit, I haven't even told you what a bit is, but 1 bit of information per horizon area in Planck units, and It is widely believed that nothing can be more concentrated than that. But what is information? What does it mean? How do we quantify it? And what would it mean to lose it? And what would it mean not to lose it? So today I want to talk about those issues, but first a little bit about the notion of a stretched horizon. Let me begin with the entropy of the thermal atmosphere surrounding the black hole. Now this is part of the entropy of the black hole. Just the, in fact in some sense it's probably all of it. But in order to understand all of it, we will have to understand the extremely hot region very, very near the horizon, where the temperature can grow to the Planck temperature and perhaps even beyond. And so when I say it's just the thermal atmosphere around the horizon, the thermal atmosphere, photons and so forth, that's a little bit too simple. But still, let's calculate the properties of a horizon as if the black hole were just a background in which we do quantum field theory. And we'll begin to see why quantum field theory leads to paradoxes. Look, we could do a very complicated calculation. It was done by Tuft years ago. It's done in that little book over there of the entropy of the thermal atmosphere. But really, it all boils down to something very simple. What it boils down to is the Stefan-Boltzmann law. Let's take the case of massless radiation in the form of either photons or any other massless particle. It could be gravitons. The thermal entropy that they carry in the vicinity of the horizon. All right, the Stefan-Boltzmann law says that for each species of massless particle, there's an entropy density. It's usually expressed in terms of an energy density, but if you use dE equals TdS, you can go straight from entropy to energy or energy to entropy. Anyway, the entropy density, which I'll call for the moment sigma, this is the three-dimensional entropy density, entropy per unit volume, according to Stefan and Boltzmann, is proportional to the temperature cubed. And then there's some constant called the Stefan-Boltzmann constant, which in natural units is just a few pi's and things of no particular interest. But there's another constant here, which I'll call gamma. And gamma is not, gamma is the constant which is the effective number of degrees of freedom, the effective number of species. The effective number of species of massless particles that we take into account. So if there's gravitons, if there's whatever the massless particles are, each one contributes a unit to gamma. But as the temperature goes up, more and more particles become effectively massless. In other words, simply stated, gamma is the number of particle species with energies, with masses below the temperature, if you like. So think of it as a function of the temperature. One fact about gamma, now I don't know if this is a theorem or not, it's something closely related to the C theorem of conformal field theories. It is widely believed, I don't know if there are any exceptions, I doubt it, that in ordinary quantum field theory, gamma as a function of temperature, and it is a function of temperature, is monotonic. That the higher the temperature, the more effective degrees of freedom that you have. I don't know, does anybody know if there's a counterexample to that? I doubt it. I doubt it. It's hard to imagine how as the temperature goes up, the effective number of degrees of freedom can go down. It's easy to imagine it the other way. Anyway, so sigma, the volume density of entropy is that. And the total entropy in the vicinity of, again, all we're going to do is think about Ringler space. We're going to think about a point near the horizon of a black hole, do the near horizon approximation, and just count up the entropy. Right? So the total entropy is equal to the integral d2x d rho. Rho is the direction away from the black hole. In other words, the radial coordinate in proper units, usual rho coordinate, and then just the entropy density. And the entropy density contains gamma, and it contains the third power of the temperature, and it's the third power of the proper temperature. You know, the real temperature that a thermometer would measure at a point rho. The last time we worked out that near the horizon, the proper temperature is 1 over 2 pi rho, and we have to cube that. All right, so the whole answer then has some constant gamma, some 2 pi's, which I won't even bother taking into account because we could absorb them easily into gamma. The integral d2x, well, that gives us the area of a patch of horizon. So that's going to give us the area of the horizon. And then the integral rho over rho cubed, d rho over rho cubed, and that's quadratically divergent. Right? Quadratically divergent. So that's the first fact about quantum field theory in the vicinity of a background horizon. The entropy is infinite. That, of course, and this is quantum field theory. This is not classical field theory. This is not the ultraviolet catastrophe of classical field theory. This is quantum field theory. And nevertheless, the horizon has a divergent infinite entropy. So H bar is not controlling this part of the entropy. It's actually G, the Newton constant, which is controlling this part. But for the moment, let's just write down the integral, and let's take the integral to go from some minimum value of rho to infinity. In other words, I'm now introducing a cutoff. I'll call the cutoff the stretched horizon. And the idea is that at distances to the horizon smaller than the cutoff, something breaks down in this integral. It could be that the horizon is fuzzy. It could be that the horizon behaves differently than a quantum field theory. Or we could simply say, for reasons unknown, the effective number of degrees of freedom goes rather suddenly to something smaller, to 0 eventually, as you get closer and closer to the horizon. But we introduce a cutoff, and that cutoff is called the stretched horizon. Let's call it from distance rho naught to infinity, and do the same integral, and of course what we'll get is something proportional to 1 over rho naught squared. All right, depending on the number of species, and if the number of species is of order 1, or it could be of order 10, or whatever it is, it's quite clear that we want to choose rho naught to be of order the Planck length. What we want is the entropy to be no bigger, or this contribution to the entropy to be no bigger than the area divided by the Planck length squared. Capital G is basically the Planck length squared, and so that tells us that rho naught is probably something of order L Planck. Let me just remind you, just in case for those who don't know, L Planck is equal to the square root of the Newton constant h bar over c cubed. It's 10 to the minus 33 centimeters. All right, so you have to cut off the, and these quanta are really there. They can't be ignored. And so you really have no choice but to cut off things at some small distance, and that is what I call the stretched horizon. Many of the paradoxes of black holes are due to the use of quantum field theory in background geometries. And the paradoxes are due to the fact that from the one point of view, the thermodynamic point of view that we did last time, the entropy of the black hole was finite. From the point of view of quantum field theory, the entropy of the horizon is infinite and can absorb an infinite quantity of information. That is the origin of many of the paradoxes, especially those which are based on thinking about naive quantum field theory in a background, especially free quantum field theory. Let me give you one more example of how physics works at the stretched horizon. In particular, I want to think about an electric charge falling into a black hole. Now, if you think from one point of view, you might think, right, here's the horizon of the black hole, a point electric charge, a point doesn't have to be a point, an electron. An electron, perhaps a high energy electron, comes through and whizzes through the horizon according to its own estimate. It whizzes through the horizon, it maintains its shape, it maintains its size, and you might think that the right picture is that the electron just makes a little dot on the horizon, a little dot of charge, point charge plastered to the horizon as it approaches the horizon. This is the wrong picture. It must be the wrong picture because eventually when a charge falls into a black hole, the black hole has no hair, and so eventually the charge has to distribute itself over the entire horizon. So there's something wrong with the picture that the charged particle just deposits a point charge somewhere on the horizon. If you wait long enough, the horizon has to come to equilibrium, and the charge has to be spread over the whole horizon. So how do we understand that? How do we think about that? Well, we can actually think about that quite classically by actually following a charge as it falls through the horizon. Not as it falls through the horizon, but watched from outside. But we have to introduce the notion of the stretched horizon. We have to stand slightly away from the mathematical horizon. Remember, the mathematical horizon is a place where there are no degrees of freedom. Gamma goes to 0. It must go to 0, otherwise there would be a divergence of the entropy. So we stand back one Planck length from the horizon, and we ask what the charge distribution at one Planck length from the horizon does as a function of time. So let me calculate that for you. It's kind of very straightforward, very easy to calculate. And we're going to find out that the horizon behaves like an electrical conductor. How does a conductor behave? An electrical conductor is such that if you put a charge into it, or onto the surface of it, more important, onto the surface of it, the charge will quickly, very quickly, redistribute itself over the surface. That's the characteristic of an electrical conductor. So let's see if we can see why that happens. Let's start with Ringler space again, because the whole problem is a problem of the near horizon geometry. All right, here is the omega coordinate. The omega coordinate is hyperbolic angle. And remember that a time translation is nothing but a Lorentz boost in the background flat space-time. Rho is the proper distance from the horizon. All right, so lines like this are constant rho, but I can also introduce a coordinate called z, and z is just an ordinary, Cartesian coordinate in Minkowski space. This is z equals z naught, and that's going to be the trajectory of the electron. Notice that it passes through the horizon at this point right over here. But I don't want to get that close to the horizon. I want to introduce a stretched horizon at some minimal value of rho. Let's work in Planck units. In Planck units, the minimal value of rho will be 1, or something approximating that. And so let's draw our stretched horizon like that. Here's our stretched horizon. And what I want to do is calculate the time dependence of the charge distribution on the stretched horizon. Now, what do I mean by the charge distribution? Let's redraw the stretched horizon by going to some other coordinates where the stretched horizon just looks like a time-like surface. The charge falls toward it. Eventually, according to this picture, the charge will go inside the stretched horizon, right at this point here. But electric lines of force will come out through the stretched horizon. Way back far out here, the electric charge has electric lines of force coming out of it, and those lines of force continue to distribute themselves out far away from the black hole. And at every point where an electric line of flux passes through the stretched horizon, we'll simply say that's a charge on the stretched horizon. In other words, the normal component, we'll identify with the charge distribution on the stretched horizon, the normal component of the electric field, the rho component of the electric field. As if
Who made that electric field?
the charge.
An image of the flowing in charge?
We're in flat space. We're in flat space-time. It's just the Coulomb field of the charge. All right, that's what we're going to calculate. We're going to calculate what the Coulomb field, ordinary Coulomb field in flat space of an electric charge looks like, but when expressed in Ringler coordinates. And it's going to be surprising a little bit. But in particular, we're going to calculate it, we're going to call the electric charge distribution the normal component of the electric field at the stretched horizon. And we're going to see how it behaves. This is a elementary calculation. It can be done by, it can either be done in an easy way by an undergraduate, or it can be done by Kip Thorne. I will give you the undergraduate version of it. It goes through at point Z naught. Let's write, well, first of all, we need to know that the Z component of electric field is Lorentz invariant. Under a boost, the component of the electric field along the boost is unchanged. Now, these lines here are just boosts of constant Z. So that means that the rho component of the electric field is equal to the Z component of the electric field at every point. This would not be true of the other components of the electric field. They transform. But the ones that we're interested in, those are the same for EZ and E rho. Okay, so now here we can easily write down what EZ is. EZ is equal to the electric charge Z minus Z naught. The charge is located at point Z naught, and then divided by, this is just the usual Coulomb law, Z minus Z naught squared plus X transverse squared. X transverse means the components of position in the horizon themselves. Okay, so X is the same X that I've introduced before, and then I think I have to take this to the 3/2 power. 3/2 power, because there's a power of length up here. We've got this is the Coulomb law, right? That's the standard Coulomb law for the Z component of the electric field. Now, the charge distribution, I told you the charge distribution was E rho on the stretched horizon. That's not quite right. There's a 4 pi, so let me put the 4 pi in there. I think this is equal to 4 pi times sigma now stands not for entropy density, it stands for two-dimensional electric charge distribution. All right, now the next thing we do is we go right to the stretched horizon. In other words, we go to rho, let's call it rho equals 1. Let's call it rho equals 1. Rho equals 1 equals the stretched horizon. In Planck units, stretched horizon. So, we have to figure out what Z is doing on the stretched horizon as a function of time. For that, we use Z is equal to rho cosh omega. Okay, that's all, and we're just going to plug it into here. But before I do so, let me go to late times. I'm going to be interested at very late times, long after, according to this diagram, the electric charge has passed through, the point electric charge has passed through the stretched horizon. Of course, we're not going to follow it in behind the stretched horizon. We're simply going to follow the lines of force on the stretched horizon. So we're going to go to large omega, which means that this is just equal to rho e to the omega, rho naught, which means stretched horizon, which we'll take to be 1, times e to the omega. And let's plug that in. All right, so that tells us that the charge distribution is E divided by 4 pi times Z minus Z naught. Well, Z goes like e to the omega. So that's just e to the omega. I'm setting rho equal to 1 for this exercise. Z naught doesn't matter after a while. Z grows exponentially. Again, e to the 2 omega downstairs plus x transverse squared to the 3/2. All right. Any questions up till now? All right, now it's useful to change coordinates x. I'm going to define a coordinate y. Let's see how I defined it. Y is equal to e to the omega x. Now I'll tell you what y is. The charge or the lines of force are going to flow out. Y is a kind of co-moving coordinate which flows out with the charge. In other words, a bit of charge or a bit of flux occupies a constant position in y. You can see that here. You can see then that the charge distribution or the charge density is e over 4 pi. Now, if you follow the omegas, you'll find e to the minus 2 omega, and then divided by 1, which I think I'll rewrite as rho naught squared, I think, plus y transverse squared. In other words, the charge distribution looks constant except for a factor of e to the minus 2 omega. Why does it decrease? It decreases because really the charge is spreading out. It's spreading out, and so the magnitude of the charge distribution is decreasing. The fact that it's spreading is shown by the fact that that y and x are related by a factor of e to the omega.
It's minus omega, e to the minus omega.
Is it e to the minus omega? Let's see.
You are constant, right?
X is bigger, yeah. E to the omega. Thank you. X is e to the omega y. X is big when y is fixed. Thank you. All right. So what this is telling you is that the shape of the charge distribution stays fixed. It grows exponentially, which is incidentally exactly the way a charge spreads in a conductor. It spreads out and decreases exponentially. You can work that out for a conductor. The way that it spreads, you can say, is why does it spread? It spreads because the surface is a conductor. How fast does it spread? That's determined by the conductivity. All right, the conductivity is the thing that tells you how it spreads. Given bit of charge creates an electric field. The electric field creates a current. The conductivity determines that current and tells you how fast it spreads. So, in fact, off this formula here, you can read the conductivity. If you know how, you can read the conductivity. I won't go through that calculation. It's really very straightforward electrostatics. And you find the famous conductivity of the horizon. The resistivity is 1 over 4 pi in some natural units per square. But I didn't want to concentrate so much on the resistance. What I wanted to show you is that if you actually follow what's going on a horizon, a fictitious surface, and maybe it's not so fictitious, just above the horizon, at a distance of roughly the Planck length, what you see is not a point charge penetrating through that point, but you see a charge very rapidly, exponentially rapidly spreading across the horizon. An interesting question is how long does it take for that charge to spread across the entire horizon? Now, to do that, we would have to do a more careful calculation in the background of a real black hole, but we can estimate it very easily. We can estimate it by asking if we start with a charge which, let's say, is no bigger than about rho naught, how long does it take for x to get to be aboard the Schwarzschild radius, for it to spread an amount aboard the Schwarzschild radius? So let's calculate that. If initially y, in other words, the size of the distribution in y here, is aboard a rho naught squared, or aboard a rho naught, that's the starting point when y is that's the smallest the charge distribution ever gets. All right, how long does it take? Well, we put in here our Schwarzschild 2mg, and for y we put in something like L Planck, and then omega is logarithm of 2mg over L Planck. That's how long in omega it takes for the charge to distribute itself over the whole horizon. But remember that omega is T over 4mg. So it's mg, 4mg is Schwarzschild time. mg log mg. That is the time scale for all kinds of things to spread over the horizon. It's believed to be the time scale for thermal equilibrium to establish itself on the, it's clearly the time scale for electrostatic equilibrium. And in that amount of time, the charge spreads uniformly as it would in a conducting material. All right, that's another example of the use of the stretched horizon idea. And it gives us such information. Now, this is the information that would be interesting to an astrophysicist. An astrophysicist is not interested in following a charge into behind the horizon. He's interested in some effective description of the charge distribution on the surface of a black hole. And this is what an astrophysicist would see watching a charge fall into a black hole, would see it spread out exponentially fast. Okay, any questions about? Yeah.
What's going on? Is it that the gravity is grabbing the energy that the falling in point charge is emitting? It's spread to the effect of this electric field all over the horizon?
Well,
what's the agent that makes that spreading?
okay, ultimately what I think it is that the horizon is very hot. From the outside, it's very hot. Because it's very hot, it's a plasma. It's a conductor. And so the seen from the outside,
What's the conductor like?
pairs. Pairs in this hot gas.
But you didn't say that you had a quantum electric field.
No, I know. So there's some classical precursor.
All they put in was
That's right.
classical charge.
That's right. There's
So
some,
what? So you have a gravity and a single electric charge.
from the classical gravity
What's
point.
going on? So what's spreading it? I can only think that it grabs hold of the energy E squared, that
Well,
gravity grabs hold of the E.
Robert, I've given you the details of the calculation. The
I believe
calculation.
the calculation.
No, well, I know. The calculation involved nothing more than the Coulomb field of a point particle in flat space.
Now, that
Now,
has energy. In the
of course it
field.
has energy. Yeah.
And that has a
Yeah, you know, you're looking for a gravitational explanation of what's happening. I don't have one offhand. It's a good question. How do we think about this from a gravitational point of view? And I haven't thought about it. I haven't really thought about it.
Is it really a gravitational effect at all? I mean, if you just have totally flat space and you take a sphere and there's a particle heading towards the center, right? You could imagine the charge spreading out on the sphere.
It's like any.
And then once it reaches the center, it's
like anything else. From the point of view of the flat space coordinates, it's got nothing to do with gravity. From the point of view of the Rindler coordinates, there's this powerful gravitational field and it's doing something. And what it's doing is spreading the charge, but I've never thought very much in detail about how it does it. Let's come back to it, I don't know. I haven't thought about it much. What I wanted to come to now is entropy and information. This is a subject, when I first started working on black holes around 1983 and so forth, for many years I discovered that most of my colleagues didn't have the vaguest idea what they meant by information. When they would talk about, that was not true incidentally of Stephen Hawking. He did understand what information meant. And it was not true of Don Page and a number of other people, but most of the people thinking about this and talking about information being lost in black holes didn't have the vaguest idea what information was. So what I'm going to do is spend the rest of the hour telling you a few things about information, about entropy, about its evolution, and its evolution in a model system which is not truly a black hole, but it's a real system that you can imagine, and how information works, evolves in a real complex system. That would give us a sort of benchmark to what to expect if black holes behave like any other things. All right, so let's begin with the idea of entropy. Entropy increases, as we all know. Now, okay, so what's the definition? Let's take a few definitions of entropy. One definition of entropy starts in phase space, XP space, with any number of dimensions. We have some system, and we don't know precisely what what classical state it's in, and so we say it's somewhere's in there, somewhere's in that phase space volume. The phase space volume I'll call V, and the entropy is simply a measure of the size of the volume V. It's basically S is equal to the logarithm of the phase space volume V. Now, V is not dimensionless. It's got units of action, but you pick your favorite action to put in the denominator here. Most people will put in Planck's action, but of course, before Planck, nobody knew what action to put there. But it didn't matter much because people were mainly interested in differences of entropy. This is not the log of the volume of space. This is the log of the volume in phase space. Okay? But now we take the law of classical mechanics, Liouville's theorem. Liouville's theorem says that the phase space volume is time independent. It doesn't change with time. So that tells us that the entropy is always exactly constant. On the other hand, the second law of thermodynamics tells us that the entropy always increases. This drove Boltzmann to suicide. I don't know if that's really true or not. No, it's not. But what does happen? Okay, so what happens is chaos. Chaos is basically the rule that tells you that for sufficiently complicated systems, the phase space volume, yes, indeed, it does stay constant, but it spreads into a very fractal kind of fractal sort of structure. I don't know how to draw it exactly. And if you keep waiting, the phase space volume will split tentacles, and they'll get thinner and thinner and thinner, and eventually you'll create, without changing the volume, you will create a extremely complicated fractal structure. I never really know how to draw it, and I suspect my drawing doesn't really capture it in real sense. But the phase space volume stays exactly fixed, and so the entropy defined in this precise form, and that's called the fine-grained entropy. The fine-grained entropy stays exactly fixed. But then there's the coarse-grained entropy, and you look at the coarse-grained entropy in the following way. You say, with my poor vision, when I look at this, I can't resolve points on this phase space smaller than a certain size. So I surround every point in the phase space with a certain minimal volume, the resolution, whatever the resolution happens to be. And then what you're going to find is quite obvious now, that the coarse-grained phase space volume, these spheres will sort of run into each other, and the coarse-grained volume will not stay constant. It will certainly not stay constant when the fractal threads of this fractal begin to get closer to each other than the coarse-grained size. Okay, that's the volume of phase space, the coarse-grained volume of phase space, which increases. And that's what the second law is about. It's about squinting your eyes, ignoring information which is really there to be had if only you could have it. So that's the bit of tension in whether or not entropy increases. It's just the coarse-grained and the fine-grained entropy. Fine-grained entropy in classical mechanics never increases. I like to say that entropy is hidden information. It's hidden information that in this case is hidden in the coarse graining. Usually it's hidden, it's detailed information which is usually hidden because the things which carry it are too small and too numerous to keep track of. That's what we usually mean by entropy. Well, I haven't told you what information means, so I haven't really told you what. But it has to do with losing track of degrees of freedom because they're simply too small and too numerous to follow. Okay, that's the coarse-grained entropy. Fine-grained entropy is a very precise concept that never ever changes, at least in ordinary mechanics. All right, so let me make a refinement now. Supposing instead of saying that the phase space volume is some definite phase space volume like V, I say that there's a probability distribution. Supposing it's a probability distribution, and now let's call it rho. I apologize for the lack of letters of the Greek alphabet. We're using the same letter rho for something else now. A probability distribution. A probability distribution on phase space. Then what is the definition of the entropy? Well, basically, it's roughly speaking a measure of the volume of that region, but we don't measure with the same strength the volume where rho is small from where it's large. So I'll write down the precise definition, and then we'll just look at it and see that it reproduces this in a reasonable situation. It's equal to the integral over the phase space, the PdQ, let's just call it integral over the phase space, of minus the probability times the log of the probability. Since the log of the probability is always less than 1, log rho is always negative, and this thing always comes out positive. Let's just check that this really gives us the same formula. Let's take the case now where rho is constant within a given volume. That would mean that it's 1 over the volume. If rho were constant in a volume, then the probability would be 1 over the volume. It has to integrate to 1. It's assumed that rho integrates to 1. So rho would be 1 over the volume. And what would we get here? We would get minus the integral. Now, rho is 1 over the volume. Logarithm of 1 over the volume, but we take into account the minus sign, that gives us log volume. And then the integral is done over this region here where rho is not 0, and that just gives us another volume. Cancel the volume here. So yes, this is a refined version. It's kind of the expectation value of the logarithm of the probability density, but it's a refined version of logarithm of volume in phase space. Now, if you have some discrete collection of entities, a discrete collection of possibilities instead of a continuous phase space, then the corresponding idea is that the entropy is the logarithm, but here's the setup. We have some discrete possibilities, all of which we know to have 0 probability except for some finite number, little n. Little n is the number of equally probable points on this discrete phase space. Then S is just logarithm of n, the number of possibilities which we don't distinguish. In other words, the number of possibilities that our probability distribution covers. Perhaps it would be the number of configurations that we can't distinguish because they're too similar to each other. All right, that's the rough idea. The more precise idea is the sum of the sum of p sub I log p sub I, the minus sign again. Again, if some n configurations all have equal weight, then we would say that p sub I is either 0 or 1 over n. And again, we would get for exactly the same reasons that S is equal to log n. All right, that's the fine-grained, or that's the entropy associated with a probability distribution. Now, in quantum mechanics, the density of probability here is replaced by the density matrix. The density matrix itself. What is the density matrix? Whatever it is, it's a Hermitian operator. It has trace equal to 1, and it has eigenvalues which are all positive. Row 1, row 2, row 3, dot, dot, dot. So in some basis, it's diagonal. Positive entries, all less than 1. Okay? One thinks of these positive entries as the probabilities for the given states in which the density matrix is diagonalized. That's the interpretation. There's some basis in which the density matrix is diagonal. In that basis, you can meaningfully speak of the probability of each of these states. And so if we use exactly the same formula on these row sub i's here, our formula is going to be S is equal to minus the trace. Trace replaces sum. of rho log rho. This is the definition of quantum entropy for a density matrix. Any questions about the notion of a density matrix? All right. If the system is in a pure state, in other words, if it's described by a pure wave function, that means that in the basis in which the density matrix is diagonal, there is one and only one non-zero eigenvalue. 1, 0, 0, 0. In that case, the entropy is always 0. Entropy is always 0 if the probability is distributed on one point and only one point. In quantum mechanics, that becomes the notion of a pure state. So you test whether a state, whether a density matrix is pure or not by calculating the entropy. Of course, that's probably not the actual way you would do it, but that would be, this would be the entropy here can be sort of a figure of merit of how impure a state is. Right? How many non-zero eigenvalues are there? And the logarithm of that is the entropy. All right, let's move on to entanglement entropy. In classical mechanics, the only reason that you ever have a probability distribution is because you may be ignorant about the system. In quantum mechanics, you may know everything that possibly can be known about a system. If the system is composed of parts, and you look at the parts of the system will be described by a density matrix, and there will be an entropy associated with it. In fact, if a system divides into two systems, and the two systems are entangled, each one of them will have an entropy, and we'll discuss in a moment what the relationship between those entropies are. Now, we're speaking now about very fine-grained entropy ideas, not coarse-grained entropy ideas. Coarse-grained really does have to do with ignorance, okay? Fine-grained, in this case, simply means if you know everything you could possibly know about the system, still, nevertheless, if the system divides into parts, the parts of it will have a density matrix. So let's again go back to our system, which consists of two parts, A and B, with coordinates alpha and beta, and wave functions psi of alpha and beta. And let's write down, first of all, there are two density matrices. There's the density matrix of the subsystem A, which is equal to psi star of alpha beta, psi of alpha prime beta. Repeated indices are summed over. I'm not going to waste our time writing summation signs. Alpha and alpha prime are open indices, and this is the alpha alpha prime component of the density matrix of A. It's an operator in the Hilbert space of A degrees of freedom, and it's summed over B. You can say B has been integrated out, if you like. Okay. That's row A. Row B is a similar thing, and it's equal to integral of psi star alpha beta, psi alpha beta prime. Summed over alpha this time. The repeated index is alpha this time. We can calculate from this the entropy, trace of rho log rho. We can calculate the entropy of subsystem A, and we can calculate the subsystem B. I'm going to prove now that and it's called entanglement entropy. The entanglement entropy is a joint property of A and B. The entanglement entropy of A and the entanglement entropy of B are exactly equal. Now, the easiest way to see this is from the fact that the eigenvalues of the two density, the non-zero eigenvalues of the two density matrices, a zero eigenvalue doesn't cut anything in this formula. So I'm going to prove that the eigenvalues, the non-zero eigenvalues of rho A and rho B are equal. Once I prove that, that proves that that the entanglement entropys of the two of them are equal. So let's do that. It's not hard to do.
Sorry, what is the definition of the entanglement entropy of A?
Of what?
What is the definition?
Trace rho log rho for A, trace rho log rho for B. Okay. Now I'll tell you a fact. if the entanglement entropy is 0, this you could all let it prove. If the entanglement entropy is 0, it means that this factorizes into a function of alpha and a function of beta. And each one is separately in a pure state. So 0 entanglement entropy means 0 entanglement. Maximal entanglement entropy is determined by the smaller of the two systems. First of all, what's the maximum entropy a system can have? The maximum entropy a system can have is if all the probabilities are equal. If the density matrix is simply so featureless that every eigenvalue is equal to 1 over n. Okay? 1 over the dimensionality of the Hilbert space. The maximum entropy a system can ever have is the logarithm of the dimensionality of the Hilbert space. Okay? That's the maximum entropy. Now, if two entanglement entropies are necessarily equal, and the maximum of either one of them is the logarithm of the dimension of the space, then no matter how big the other system is, the maximum entanglement entropy it can have is determined by the smaller system. That's something important to keep track of, keep in mind. You can have a giant system and a small system. The entropy due to entanglement is maximized, cannot be bigger than the logarithm of the dimensionality of the smaller Hilbert space. Okay? That's going to play a rather powerful role in thinking about black holes. The big space and the small space, incidentally, in that case, the black hole is a small space, the rest of the world is the big space. Okay, let's prove our theorem. Let's first write down the eigenvalue equation for rho A. I could just tell you this is true, but let's work it out. It's not very hard. Rho A, let's write down the eigenvalue condition. So here's the density matrix, psi star of alpha beta, psi of alpha prime beta. Beta is a dummy index, and we multiply that by a purported eigenvector, let's call it phi, of alpha prime. This is the eigenvector of the A density matrix. And if it really is an eigenvector, then it should be equal to lambda times phi A. That is the condition for an eigenvector of rho A. Okay. Now I'm going to tell you, it took me about 10 minutes to guess what the corresponding eigenvector of rho B is with the same eigenvalue, and I'll tell you what it is. Let's call it, let's see, what did I call it? I call it chi. Chi has a label B. Let's call it as a function of beta prime. And it is equal to psi star of alpha prime beta prime phi star of alpha prime. I cannot remember why the stars are there. I think it's some notational glitch of mine that I've got the stars there, but I think it's right though. Here's an object which is a function only of beta prime. It's constructed from a particular eigenvector of rho A, all right? But it's constructed by multiplying it by the wave function of the combined system as a function of alpha prime and beta prime. Right? So this is a vector which corresponds to the vector on this side. If you now write the eigenvalue equation for the B, let's see what that would look like. Let's write the B equation. Here's the B density matrix, psi star of alpha beta, psi of alpha beta prime. This is a function of beta and beta prime. Alpha has been integrated over. This is rho B. Okay? We multiply this by chi B of beta prime. Then use the definition of chi B. Right? Use the definition of chi B, and then use the fact that phi is an eigenvector of rho A, and it'll pop out for you. I'm not going to do the algebra. Just plug in here this formula, you'll see then that you'll have an extra psi star. That extra psi star will stand next to this psi. That will wind up giving you rho A. All right? In other words, this combined with this will give you rho A acting on phi A, and that's the eigenvalue equation for phi. You put it all together, and you discover that chi B, as long as lambda is not equal to 0, chi B is also an eigenvector of rho B with exactly the same eigenvalue. If the eigenvalues of the rows are all the same for A and B, then the entanglement entropy is also equal. And so, and therefore, the entanglement entropy is maximized by the smaller of the systems. Smaller means smaller Hilbert space. Okay, any questions about, good. So we now have a theorem. I have no idea whose theorem this is, but I'm sure it's somebody's theorem. Scott, you know what this stuff means here?
Just say it's linear algebra.
Right, right. But somebody must have first noticed that the degree of entanglement of A with B is the same as the degree of entanglement of B with A. So SA equals SB, and if I don't put any other notation, I mean the microscopic fine-grained entanglement entropy when I write S. SA is equal to SB. Now, this kind of entropy is not additive. How do I know it's not additive? Well, if the AB system, the combined system, is in a pure state, then the entropy of the A plus B system, this does not mean SA plus SB. It means the von Neumann entropy, or the if the AB system is in a pure state with wave function psi AB, psi alpha beta, then its entropy is 0. Despite the fact that SA and SB are not 0. So this kind of entanglement entropy is not additive. And that's important to remember.
I didn't understand the statement that SA is equal to SB. And what you proved on the blackboard is that for each eigenfunction in A, there's another one in B.
With the same eigenvalue.
Eigenvalue. But the Hilbert space may be of a different dimension.
Doesn't matter. For all the non-zero eigenvalues match. And then the bigger system will have more zeros. Okay, but they don't contribute to the
But they
to
don't
X.
contribute to the entropy.
Right, they don't contribute to the entropy. Right. Yes, you understand it. Good. Okay. Okay, now let's take a big system, a really big system with a lot of parts. For simplicity, think of all the parts as the same. And divide it into a lot of parts. Let's first of all imagine that the big system is in a pure state. It could be an energy state, an energy eigenvector, or it could be in some other state, but the expectation value of the total energy is some number. Let's just call it E. It doesn't matter, it matters whether it's in a pure state. It does not matter for the moment whether it's an energy eigenvector or not. All right. This, I am not going to explain the following fact. This is something which is explained in every thermodynamics, statistical mechanics textbooks, and the explanations are always wrong. I don't really know how you prove it. If you take a small subsystem in a big part of a big system where the energy is known, and you calculate its entanglement entropy with respect to the rest of the system. The entanglement, and I'll tell you eventually what I mean by a small system. It basically means one less than half the size of the whole system. But a small system, then the density matrix, the entanglement density matrix, is just the thermal density matrix. Rho sub I is equal to e to the minus beta h sub I Now, there are some caveats. You have to be thinking about fairly weakly coupled systems so that you can identify a well-defined concept of the energy within the subsystem. Weakly coupled subsystems. The point is, weakly coupled subsystems like this come to thermal equilibrium. Experimental fact for almost all states. And even if you put the system in a well-defined energy eigenstate, small parts of it will look thermal. And so for a small part of the system, you can be quite sure that the entanglement entropy, S, is equal to S thermal. S is equal to S thermal pH for small subsystems. I'll have to try to quantify small later. Small turns out to be not so small. Okay. That's one statement. Now, next definition. The definition of the thermal entropy of the whole system is just add up all of the thermal entropy of the subsystems. It is not the, no?
No? Okay, is the big system isolated?
Yeah, let's assume big systems isolated.
Constant energy?
Yeah.
So then it can't be.
What can be?
That the entropy is the sum.
No, the thermal entropy. Definition. This is new definition. Thermal entropy. Thermal entropy, and it is the thing that a thermal, no. The thermal entropy of the big system is by definition, just the sum. And if you don't like it, I'm only going to use it as a definition. I'm never going to use it in any other way. All right? But it's a standard definition. Thermal entropy of the whole system. Let's call the small system sigma 1, or subsystem. The subsystem is sigma 1. For a small sigma 1, S is equal to S thermal. For the whole system, definition, S thermal, is by definition the sum of S thermal for the small systems. Now, if you don't like that definition, just give it another name. Call it the sum of all the sum of all the little entropies. And it doesn't matter whether we call it or not. That's going to be its name. The thermal entropy for the whole system.
So does this depend on what kind of small systems you choose?
What's that?
Does that depend on what kind of small systems you choose? Whether you choose small ones or slightly bigger ones?
It turns out it doesn't depend on. That's the point. It doesn't depend on how finely you divide it up.
It's just that the coupling between the subsystems is very weak.
The coupling between the subsystems is very
That
weak.
doesn't
Right.
contribute to
Right. Roughly speaking, these subsystems can be almost as big as half the system. It'll still work. It's a remarkable fact. Incidentally, the reference for much of this comes from a paper which should be an extremely famous paper. I'm afraid it's not my own paper. It's a paper by Don Page called Entropy of a Subsystem. And it's an extremely beautiful paper, a series of them. It's a real tour de force in demonstrating the properties of entropies of subsystems. So far, I haven't even gotten to what it was that Don Page said, but we're just making some definitions. Okay. Now, here's another fact. The entropy of any subsystem is always greater than, no, the other way, always less than or equal to the thermal entropy. In this kind of context, where you have a large number of systems collected. So the thermal entropy is typically bigger than the whole entropy. For example, if you looked at the whole system, the fine-grained entropy of the whole system, in other words, not the thermal entropy, is 0 if it's in a pure state. With my definition of the thermal entropy is always bigger. So all entropies, fine-grained entropies, as you might expect, are smaller than the corresponding thermal entropies. These are facts. I'm giving you all the facts that I know about entropy. Okay, now, what is information? Information and entropy are very closely related. one definition of entropy, which is, I suspect it's useful for information theorists, is just to say, well, some people just say it's minus the entropy. That sounds stupid. Why bother? The way I like to say it is it's the maximum entropy the system can have less the entropy. The difference between the maximum entropy that the system can have and the actual entropy. That's what's called information. But in most systems, there's no such thing as the maximal entropy. You know, the entropy of a quantum field theory can be arbitrarily high. So I define a little bit different, and I'm not sure, I think this may be a standard definition, I'm not sure. But I define the information to be the difference between the thermal entropy of a system and the actual fine-grained entropy, which may be the entropy presumably coming from entanglement, but calculated very precisely from some pure state. This is what I call the information. The difference between the thermal entropy. The thermal entropy is always bigger, and the actual entropy is called the information.
Sorry, I'm confused. So you initially said that for a small enough subsystem, the entanglement entropy equals...
Say it again?
So for a small enough subsystem, the entanglement entropy equals the thermal entropy.
For a small subsystem.
And then you say if you...
Yeah, for a small subsystem, the information is always zero.
Yeah, sorry, so my question is there. So then you say that the thermal entropy is the sum of all of these guys.
Yeah.
So what does the next line mean? As subsystem is less than S thermal?
Well, if you take any subsystem and you calculate its thermal entropy by adding up all the little entropies, all right, it will always be bigger than the actual entanglement entropy of the system. And the limiting case is very clear. The limiting case is where you cover the whole system, where the actual entropy is completely zero, but the thermal entropy may be big. Okay. So by covering bigger and bigger pieces of the system, you get typically smaller and smaller entropies if you're in a pure state. And that's the way to think about it. If you're in a pure state, the more you know about the more... Another way to... Okay, that will do. That's, all right, so the information is the difference either between the maximum entropy that a system could have and the actual entropy it has, or if you don't like to think about maximal entropy because systems typically have an infinite amount of maximal entropy, you can use the difference with the thermal entropy, and that's the one I like. Other people will simply say minus the entropy. Any one of them is okay, but I like the difference between thermal and...
So if you refer to some temperature, right? For in your definition.
Some pure state for the entire system. Some pure state for the entire system, which will in general determine an average energy. Okay. Right. The whole system will not really look thermal. It's clear it won't look thermal. It may be in the microcanonical ensemble with a very definite energy, or it might be some superposition of states with different energies but not thermally distributed, but small subsystems will look thermally distributed. And well, I'm always going to imagine that the big system is in a pure state of some kind. So always imagine for all the purposes that the system is in a big. Okay. Now, small systems have very little entropy. What about big systems which are large fractions of the whole system? Can we quantify how much entropy they have? And now I don't mean thermal entropy. Unless I say thermal entropy, I mean precise entanglement entropy. Well, we get a pretty good idea. Let's take a system, divide it into two parts. One, which we'll call sigma 1, which I'm thinking of the bigger part, but I can also think about it as a smaller part if I want. And I'm going to say that that's f times sigma. Now, f simply means a fraction. I'm imagining all the degrees of freedom are identical to each other, and f is just a fraction of degrees of freedom that are in sigma 1. Right? Sigma 2 is sigma minus sigma 1, and it is equal to 1 minus f times sigma. The fraction f just tells you the fraction of the number of degrees of freedom that are in the subsystem sigma 1 or sigma minus sigma 1. Okay? Now let's suppose that sigma minus sigma 1 is a small system. That sigma minus sigma 1 is small enough, really all it has to be is a little less than half the whole system. But let's say we know that it's a small system, in which case the entropy in here will be the thermal entropy. Will be the thermal entropy in here. And the thermal entropy in here will be 1 minus f. This is the entropy of sigma minus sigma 1. That will be 1 minus f times the total thermal entropy. But we also have a theorem that tells us the entropy in 2, or in sigma 1, is the same as the entropy in sigma minus sigma 1. That's this theorem about entanglement entropy. So we can immediately conclude that in the bigger system, S of sigma is also equal to 1 minus f times the thermal entropy. So first of all, if f grows to 1, in other words, if this system becomes the whole system, the von Neumann or the precise entropy goes to 0, as it should. Okay? On the other hand, if f goes to something very small, then, well, this was a calculation for a big piece of the system. All right. So let's draw a plot now of what, as a function of f, what the actual entropy of a subsystem looks like. All right. It starts out being proportional to f. Why is it proportional to f? Because for small subsystems, it's just the thermal entropy, and the thermal entropy will be proportional to the number of degrees of freedom. So it starts out the small f being proportional to f. It ends up at the other end being proportional to 1 minus f. Somehow it's connected together in the center here. What Don Page showed was really quite remarkable. What he showed is, let's start, let's take that. That's the, yeah. What he essentially showed is that it basically looks like this. That it continues along the thermal line until you have just about half the system. At half the system, it turns over very quickly, and the information starts, or the entropy starts going back down. This is a very interesting paper to read. I advise you to read it. But this is the basic picture that Don Page came up with for the entropy of a subsystem. It increases linearly with the number of degrees of freedom until it gets to about half the degrees of freedom, and then it just turns over. We can calculate the information. The information in a small subsystem is 0, because for a small subsystem, the entropy is thermal. What about for a big subsystem? All right, so let's calculate the information in the big subsystem. It is the thermal entropy in the big subsystem. That's F times S thermal. F is the fraction of degrees of freedom in the big system, minus the entropy, minus 1 minus F times S thermal, which is equal to 2F minus 1 S thermal. So if I plotted the information in a subsystem, well, it would be 0 until you get to about half for the small subsystem, and then it grows linearly like that. No information for all practical purposes when you look at half the degrees of freedom. They simply look thermal. And then as soon as you get to about half the system, the information starts growing linearly until it gets up to S thermal. When it gets up to S thermal, that's it, you've covered the whole system. So if you have a pure state with many, many parts, the information in the whole system is just S thermal. Okay, that's the, in that sense, entropy is hidden information. Yeah.
Well, I wonder what, I thought that tent map was for the finite entropy.
What's it, say it again?
The tent map that you showed there,
The
well, that's what you stand in front of. This what you have shown
This,
there.
yes.
This is for the finite entropy.
That is.
Okay, I wonder what assumptions go in there. Is it for a generic initial state? Because
Yeah,
if you
that's
use
right, that's right.
ground
What,
state-
no, that's exactly right. What Don Page did was he showed that for all but a set of measures zero states, this is what you have. Right, exactly. Obviously, there are states which violate this. Right? So what he did was he explored the Hilbert space with some Haar measure on the Hilbert space, and found that for all but a set of measure zero on that large Hilbert space, what he actually studied was 2 to the nth states of n spins, and showed that for all but a set of measure zero on the Hilbert space of that space, of that system, that the information in the subsystem was typically zero. Okay, so this is a picture for the overwhelming majority of states of the system, of a big system. And as I said, I strongly recommend the paper. All right, let me finish up by talking about a process which is in some sense analogous to a black hole evaporation, but not a black hole evaporation. A real system that we could do in the laboratory, but we might want to stand back and not get too close to it, and follow the various entropies. We have a box. The box will be labeled B. B stands for 3 things. It stands for box, it stands for bomb, and it stands for, later on, of course, it will be the black hole. Okay? And then there's a subsystem A, which is the outside, consisting of everything else. There's a tiny hole in the box, which lets radiation or other evaporation products out. I want to follow the time sequence of the various entropies and show you what they look like. And in doing so, I think we will get some sort of benchmark for what we should expect for a black hole and how it evaporates, assuming that it evaporates and behaves like the most generic systems we can think about. This is a very generic system. I'm not going to assume anything very special. All right, let's start with the initial state. Initial state, the bomb, incidentally, is at 0 temperature, no entropy at all, absolutely in its ground state. A is empty space, vacuum, and so initially, in the initial state, SB equals SA equals S thermal of A and B, and everybody is 0. All entropies are 0 to begin with. Everything is in its ground state. Okay, the bomb explodes. Later, soon I'll draw a graph of what it looks like, but let's just follow a sequence of steps. Bomb explodes. Okay. SB thermal gets big all of a sudden, fast. The thermal entropy inside the box that everybody will agree is large. Everybody but Robert will agree that the thermal entropy inside that box is large. At least with my definition, it's large. You break up the box into small pieces, you'll find lots of entropy in them. And so the thermal entropy in B will be large. What about the fine-grained entropy in B? The fine-grained entropy in B will be exactly 0. Why is that? Because the fine-grained entropy of A is 0. So far, no photons have leaked out. This is before any photons leaked out. We're still in absolutely the vacuum. Fine-grained entropy in A, fine-grained entropy in B are equal. Another way of saying that the box is still in a pure state. So SB is still 0, and SA is still 0. Photons begin to leak out. Photons or other evaporation products begin to leak out. When a photon begins to leak out, the inside and the outside become entangled. For example, you could have a quantum state which is a linear superposition of no photons on the outside, all the photons on the inside, and then one photon on the outside, n minus one photons on the inside. That becomes an entangled state. So the inside and the outside begin to become entangled. As they become entangled, the entanglement entropy increases. So photons leak out. What happens? The thermal entropy, S thermal in B, decreases, of course. Everything's leaking out of B. S thermal of A begins to increase. The hot gas begins to move into the region A. That starts to increase. What about the entanglement entropy? I need not write whether it's entanglement A or entanglement B. They're the same. The entanglement entropy also begins to increase. Increases. Okay, now let's go to the final state. In the final state, all of the photons have leaked out. So over here, the final state. Final state. In the final state, everything is leaked out. The box B is in its ground state. SB equals S thermal B. My notations are probably not consistent, but all right. Equals 0. What about SA? SA thermal is certainly not 0. The thermal entropy of A is certainly not 0. It's all those hot photons. And there's a stream of photons going out. If I divided it up into blocks, I would find that they were entangled with each other. If I added up all the entanglement entropy in A, I would have a huge amount of thermal entropy in A. And in fact, by the second law of thermodynamics, the thermal entropy in A would be bigger than the original thermal entropy in the bomb. Okay? But the entanglement entropy, SB and SA, are both equal to 0. How do I know that SA is equal to 0? Because SB is equal to 0, and they're equal. Okay? So this is the history. The history is from a pure state of the box to a pure state of the outer world, and in the end, all entropies are equal in the beginning and equal to 0. In the beginning, all entropies are equal to 0. Let me draw you a graph of what it looks like. And then one last concept, which I think is a very important concept, for reasons that I don't know. Statistical mechanics have not, statistical mechanics meaning the human statistical mechanics, don't seem to have taken up the challenge to figure these things out. Nobody's really very interested in the precise, exact, fine-grained entropy of a big system. What use does it have, except showing that black holes don't violate quantum mechanics? And most of my friends who work on statistical mechanics, like Joel Leibowitz, don't really care about black holes. So there's some really interesting mathematical analysis to be done. Okay, what does a graph look like? Let's first graph the thermal entropies of the two systems. Here's the thermal, S thermal of the two systems. Let's first take the box. At first, everything is 0. Then the bomb explodes. Sudden increase in the thermal entropy in the box. All right? And then the photons leak out, and it gradually goes to 0, the thermal entropy. What about the outer world? At first, the outer world has no photons in it. Depending on the hole in the box and how big it is, Photons start to leak out, and as they leak out, the thermal entropy of the outer world starts to increase, and it eventually increases a little bit bigger than, not necessarily a little bit, perhaps a lot bigger, but it will get bigger than here because the final entropy must be bigger than second law sorts of things, thermal entropy. So this is box, this is outer world A. Eventually the box thermal entropy goes to 0, the thermal entropy in A becomes big. Okay, now what about the von Neumann or the entanglement entropy? The entanglement entropy must be smaller than the thermal entropy, but it must be smaller than either of the thermal entropies, okay? Because, well, for obvious reasons. So the entanglement entropy must stay below this line, and then it must stay below this line. The thing that Don Page showed is just that it hugs these lines very, very closely until about that point where there's about half a bit of information, no more. It only differs by a half amount. So the entanglement entropy looks about like that. What about the information? The information is the difference between the thermal entropy and the entanglement entropy. So in the beginning, we have a lot of information in the box. The information in the box decreases, but the information in the outer world starts to increase. Eventually, the information in the outer world becomes equal to the thermal entropy of A. That's the flow of information, that's the time dependence of the various kinds of information that take place when a bomb explodes inside a box. Now, there's an important time scale. The important time scale is right over here. It is the point where the information begins to show up in the outer world. Before here, there's essentially no information in A. A is the small system, and there's essentially no information in it. It's at this point here, this crossover point, where the first bit of information, or the first few bits of information, start to show up in A. That's long after many photons have been emitted. It takes many, many photons, basically about half the entropy, half the whole total thermal entropy, before the first single bit of information comes out in the outer world here. So information is not something which dribbles out of this box from the beginning. Information takes its time, and it doesn't begin to come out of the box. In other words, it doesn't begin to appear outside the box until this time, and that time is called, probably only by me, the information retention time. In other words, the time that it takes for information to appear on the outside, the information retention time. It's a very interesting mathematical thing to explore. It has not been explored except by Don Page. And the question is, how long a time does it take before you begin to see information? The answer for a black hole, if it follows the same pattern, would be it takes an amount of time for half the entropy to dribble out of the black hole. That's a very, very long time. So we don't expect to see it dribbling out except very, very slowly. Okay, that's all the information I have to tell you.